In this video, we'll look at weak electrolytes. A weak electrolyte is probably a compound then that doesn't conduct a lot of electricity. And in order to not conduct a lot of electricity, there must be a low tendency of forming ions. We mentioned earlier that the more ions you have, the greater the conductivity. So here, these are solutions that just don't have a lot of ions. Often, they're polar covalent compounds. Here's kind of an example. This compound is an alcohol, C2H5OH. At this end, this carbon with 3 hydrogen end, pretty nonpolar. The electronegativities between carbon and hydrogen are similar. So the region that I'm really concerned with is this OH group on the end of the alcohol. It's a very polar region, which we kind of mentioned earlier with water, that the oxygen-hydrogen bond is very polar. The electronegativities are very different. So the electrons in that bond are drawn closer to the oxygen, making the oxygen partially negative and leaving the hydrogen partially positive. So enter in a water molecule. You put this thing in water and there is attraction, but only from this group right here, while the oxygen was a little negative and the hydrogen was a little positive, and that's similar to a water molecule. Now the oxygen is a little negative and the hydrogens are a little positive. So yeah, this makes sense, right? That there is attraction between the partially positive hydrogen and the partially negative oxygen. Attraction. So these compounds are going to mix together very well because of those attractive forces. But a polar covalent compound, or any covalent compound for that matter, doesn't normally contain ions. Ionic compounds contain ions because ions are formed from the transfer of electrons, where you get one particle that is completely positive and one that is completely negative. And we're not going to have that here. There is an attractive force, but it's not so strong that I'm removing ions from a crystal structure like we did with the ionic compound. There's only one chance that ions could form in this situation. And it's like the stars have to be perfectly aligned. If these particles are in the right place at the right time, in the proper orientation, so that this partially positive hydrogen is close to the partially negative oxygen, and they're just in close proximity to each other, because obviously in solution they're kind of moving around, so they would have to be oriented in this fashion, and they'd have to get really close to each other so that this attractive force could become really significant. There is a chance that if the attractive force was strong enough, this hydrogen could be completely removed by that negative oxygen, where this little baby hydrogen gets ripped off its original molecule and it becomes part of the water molecule. But again, that doesn't happen very often. In order for that to happen, we have to have these particles in the right place at the right time in the proper orientation, really close to each other, so that we can maximize that attractive force. If that happens, an equation might look something like this. Plus water. On the product side, this hydrogen is being removed and attracted to the oxygen end of the water molecule. So all you're left with from the original compound is C2H5O, and then instead of water it becomes H3O. Now these products would not be neutral. Hydrogen is positively charged, So with an extra positive hydrogen, this H3O becomes +1. And if this guy is missing his hydrogen, it becomes -1. If you had to write an equation, we might write it looking something like this. But now here's the deal. This does not happen all the time. With the ionic compounds, we said it was a 100% dissociation. Everybody splits. If you start with 100 molecules, you get 100 ions. Maybe not the case here. Let's say initially I have 100 molecules. And initially I don't have any of these products. If this happens, where I transfer that hydrogen, it might be 1 out of 100. This might go down to like 99. And maybe this would be 1 and 1. And these would be ions now because they're charged. Oopsie, I'll just say ion. And this would be 1 ion. It's a little different than those ionics that were 100% dissociation. This might be like a 1%, where most of the particles are still neutral, which is why we call these weak electrolytes. Will it conduct electricity? Sure. Do I have charged particles? A little bit, but most of them are still neutral. So the conductivity will be low. This just doesn't happen all the time. Everything has to be perfectly aligned in order for that oxygen to be so attracted to the hydrogen that it completely removes the hydrogen. Here are a couple other examples. And I like this visual because it kind of shows what's happening in a weak electrolyte. In a weak electrolyte, you'll have mostly neutral molecules. Most of these molecules are still neutral. There's maybe only one in each case that's split. That's just not going to conduct a lot of electricity because you don't have a lot of moving charged particles. We're going to test acetic acid and ammonia in the lab. Yeah, they'll conduct, but not very well. Weak electrolytes. Up on top, they want me to write equations for these reactions with water. Now here's another thing that's a little bit different. When we were writing dissociation equations, we never put the water in the equation. If it was ionic, we just showed something like sodium chloride splits to form sodium ions and chlorine ions. We never put water in the equation because the water never changed. The water stayed neutral H2O molecules that just eventually kind of surround each ion. But water doesn't change, so we don't really need to put it in our equation. But in this case, the water is a little bit different. So we do put water in the equation. Now this might make you feel a little better. You will never, ever, 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 ever need to write these equations. They'll be written for you. We just have to identify that, oh, this is the equation for a weak electrolyte. There's often a reaction with water. So look at this acetic acid. COOH in water. It's a very similar situation to the last example. That the oxygen of the water molecule is very negative. It'll be attracted to that hydrogen that's dangling off the end of the acetic acid molecule. That is, again, a polar bond. Over here, this OH group is very polar. So that hydrogen on the end is vulnerable. It's not being held very tight to the original molecule. If the attraction is great enough, we could remove the hydrogen. So we'd be left with CH3, COO, which looks kind of funny, but it's right. And then H3O. And these particles would be charged with the extra hydrogen. H3O is +1. Without the hydrogen, the rest of that original molecule is called the acetate ion, and it is charged -1. Often, with weak electrolytes, you'll see water on the reactant side, because the water does change a little bit. So we do put water in the equation. Here's ammonia. Ammonia, NH3 in water. Here's what happens, and again, you never have to write this yourself. The nitrogen has a pretty high electronegativity. It's got a lone pair of electrons. One of the hydrogens from water will be attracted to that nitrogen. So that on the product side, you'd have NH4 instead of NH3. And if only one hydrogen is transferred, you'd be left with OH. Just a hydrogen and an oxygen. Now these particles might look a little familiar to you. OH, which will now be -1, is hydroxide. And H4, which will now be +1, that's the ammonium ion. Again, you won't have to worry about like that transfer of electron thing, or transfer of hydrogen, trying to predict all of that. I'll give you these equations. If we see something like this that splits right away, that's a strong electrolyte. It completely forms ions without the help of water, because ions were present in the original ionic compound. If the original compound is covalent, meaning all nonmetals, it'll have to react with water first in order to form any kind of charged particles. And this just won't happen very often. This might be a 1% dissociation. So most of the molecules are still neutral. Pretty crazy stuff, huh? We're going to look at these in the lab. We're going to test them and work with them more so that we kind of get used to these weak electrolytes. Often covalent compounds that have to react with water in order to form any ions and conduct a little bit of electricity. But if this doesn't happen 100%, we'll have a low amount of ions and we'll conduct a low amount of electricity.